Okay, let's welcome the second speaker. Matthew is going to talk about enriched retro functions and lenses.
Cool. Should I use this one or that one? All right. So maybe I should start by thanking Bryce and Sam for actually organizing this iteration of SYCO. It's been a lot of fun. Been lovely to meet some new faces and see some old faces. So some of you might be wondering, well, given that I've told you that I'm working with Chris on dagger category stuff, what enriched cofunctors and lenses have to do with that? And I guess the answer is they don't. So this goes back to work that Bryce and I started when I was at Macquarie University. Well, when we both were at Macquarie University 2 years ago. So we were both working with Mike Johnson on delta lens kind of stuff. If you don't know what a delta lens is, don't stress. We will talk about that in a moment. But we were working on this stuff, and we had this idea for how we could actually generalize the notion from the setting of just ordinary categories, so delta lenses are morphisms between categories, to the setting of enriched categories. And I mean, at the time, you know, we had this idea. We thought, oh, that's cool, but we were busy with other things. We didn't get around to sort of writing it up. And then last year, at some point, Paolo Perrone put out this paper where he introduced the notion of weighted lenses for the purposes of categorical probability theory. So and this was a bit of motivation for us to actually write up what we had worked out about enriched lenses, because these weighted lenses are an example. But it turns out there's a whole bunch of interesting examples of these notions, and so I think it's sort of interesting because it brings together a bunch of different things from different parts of mathematics that have this similar kind of flavor of like a lifting and some kind of compatibility. But again, we'll talk about that momentarily. So I guess just to sort of outline what I'm hoping to achieve with this talk, it's to give you a sense, sort of like an intuitive sense for what these enriched cofunctors and lenses are, without sort of going too much into the details of the definitions, because I mean the definitions involve a lot of diagrams that have to commute, and if you sort of look at them, and you might not really get a feeling for what it's about. So I'm going to give a whole bunch of examples, and if then at the end you're interested in more sort of concrete definitions and results and things, then we can direct you to the preprint that we have on the archive. So the last thing I should say whilst we're here is you'll see that I've crossed out the co on cofunctors and wrote retro, and this is because we're trying out a new name. So when I say cofunctors, probably most of you think about contravariant functors, which is not actually what we mean by cofunctors. So cofunctors are a kind of morphism between categories where you have well, I mean, I'm going to explain it in a moment, but they're more about lifting morphisms than it's not the same thing as a contravariant functor. And so we're trying out this new retro prefix, which has been taken from some work that Bob Perrone did, where in some other setting it's sort of related, and where we think that the name, or at least I think that the name retrofunctor is maybe a less confusing term than cofunctor. But anyway, maybe by the end of the talk we can have some feedback on whether you think that's the case. But let's start with I mean, this is the example that Bryce and I were originally sort of interested in before we did all this enriched stuff, and that's the ordinary category setting, or the set enriched setting. So in this setting, I mean, we're all familiar with the notion of functor, I hope. So a functor, we have a mapping on objects. So we map object A to an object f of A. And we have a mapping on morphisms. So we can map morphisms f to morphisms f of f. And obviously, I mean, there's a bunch of compatibility conditions and it has to respect identities and composition. But this should all be familiar to everyone. But maybe this notion of retrofunctor, sorry, I keep moving the microphone around. So this notion of retrofunctor may be a bit less familiar to people. So a retrofunctor phi from C to D, again, has an object map. So for objects in C, we can apply phi to get objects in D. But retrofunctor, instead of also mapping morphisms in the same direction, it involves a lifting of morphisms. So if you're familiar with notions like discrete off vibration, split off vibration, so these notions involve lifting, but in that setting, the lifting is canonical, so it's determined by some kind of universal property. Whereas in this setting, the lifting is a structure. So for every object A and C, and every morphism G out of phi of A, we have a chosen lift, which here I'm denoting phi superscript A of G. And the target of that lift has to lie above the target of G. And then what you ask is for, I guess we could call it retrofunctoriality. So it should lift identities to identities and composites to composites. So this is the notion of retrofunctor, or if you go Googling for it, you'll find the notion of cofunctor, but I explained why we're calling them retrofunctors today. And so we have the notion of functor, and we have the notion of retrofunctor, and then you can bring them together. So if I have, say, a functor f and a retrofunctor phi between the same pairs of categories, such that their object maps are the same, and there's some compatibility condition between the action of f on morphisms and the lifting of phi on morphisms. So you sort of, the condition is if you lift via phi and then you apply f, you get back to what you started with, then the result is called a delta lens, or more specifically an asymmetric delta lens. And so this is the starting example from which we're generalizing. Okay, so as I said, so early last year, Paolo introduced a notion of weighted lenses. And so these are very similar to delta lenses. So again, so what is a weighted category, I guess, is where I should start. So a weighted category, it's a category where to every morphism we associate a weight, which is some number in this interval 0 to infinity. And then these weights have to sort of be, they have to respect composition and identities in an appropriate way. And so a weighted functor is, it's a functor between the underlying categories of these weighted categories, but it has to respect the weights as well. So I guess it's non-increasing in weights. So if I have the weight of f should be less than or equal to the weight of f. So that's a weighted functor. And you can also define the notion of weighted cofunctor or retrofunctor. So here, again, it's just a retrofunctor between the underlying categories, such that the lifts are non-increasing in weights. So the weight of the lift of G should be less than or equal to the weight of G. And again, if you take a weighted functor and a weighted retrofunctor, and then impose some compatibility conditions between these two things, you get a notion that Paolo introduced, which is this notion of weighted lens. So I hope it's fairly clear how this particular example generalizes the one we saw on the previous slide. But now I'm going to give you some more examples that may seem a bit different, but still have the same kind of flavor. So here's the next interesting example. So we're now talking about Levere metric spaces. So these are metric spaces, but where we're allowing distances to be infinity, and we're not necessarily imposing that the distances are symmetric, so the distance from x to y, not necessarily the distance from y to x. And so in this setting, we're probably all familiar with the notion of a non-expansive map between metric spaces. So with a non-expansive map, if I have 2 points x and a in my codomain, and then I apply my non-expansive map to them, then that should not increase the distance between the points. So the distance between f of x and f of a should be less than or equal to the distance between x and a. And another way of sort of thinking about this is that our non-expansive map should map the open ball of radius r into the open ball of radius r. So that's a non-expansive map. Now, this notion of retro non-expansive map, we've invented this terminology because, I mean, we're not familiar with a name that corresponds to that in the literature. So what is a retro non-expansive map? Well, it's kind of like a non-expansive, well, it's a map that's non-expansive in the other direction. So if I have a point x in x, and I have some other point y in y, then the distance from 5x to y should be greater than or equal to the infimum over all points in the pre-image of y of the distance between x and that point. And if you sort of play around with this definition, it's equivalent to saying that, what is it? That if I take the open ball of radius r, and I look at its image in phi, that should contain the open ball of radius r in around the image of x. So you can sort of see that there's some kind of duality between these two definitions. And I guess the interesting thing here is if we take a non-expansive map and a retro non-expansive map, and in this case, we don't actually need to, well, sorry, I guess the only compatibility condition we need is that the maps are the same map. But, you know, in terms of, because we're sort of, you don't actually need any additional compatibility conditions other than that. But when you put them together, you get this notion that's known as a weak submetry, which is a thing that is, I guess, known about by certain people who study metric spaces. But yeah, it's kind of interesting that this notion that people have studied before comes out of this kind of this idea of having maps that not only sort of act in the same direction but have this kind of lifting kind of behavior. Okay. So for another example, we're going to talk about Alexandrov discrete spaces, or equivalently, pre-ordered sets. So I hope we're all familiar with the notion of a pre-ordered set. So a set equipped with a binary relation that's both reflexive and transitive. So it's sort of almost a partial order, but not necessarily anti-symmetric. And well, there's some kind of equivalence between this notion and this. So an Alexandrov discrete space is a kind of topological space where not only finite intersections of open sets are open, but arbitrary intersections of open sets are open. And there's a way of going back and forth between these two notions. So from pre-ordered sets to Alexandrov discrete spaces, you take the upwards closed sets as the open sets of the topology that you put on your space. Going the other way, you can define, so if you have an Alexandrov discrete topological space, you can define a pre-order on that space in terms of saying that I think it's something like x is less than or equal to y if the neighborhoods of y are contained in the neighborhoods of X, or every, something like every open set that contains X contains Y or something. I probably haven't quite gotten that right, but if you're interested, it's not hard to look up online the correspondence between these two notions. So, I mean, on the preordered set side, the usual notion of morphism between preordered sets is this notion of monotone maps. So if I have X is less than or equal to X prime, then f of X is less than or equal to f of X prime. And under this correspondence between preordered sets and Alexandrov discrete spaces, this notion corresponds to the notion of continuous map. So, I mean, there's various ways to formulate what a continuous map is, but one of them is that the preimage of every open set is open. So, on the other side, so for topological spaces, there is a known alternative kind of morphism between topological spaces that people are interested in, maybe less interested in than continuous maps, but still interested in nonetheless, and that's the open maps of topological spaces. And when you sort of pull the open maps of topological spaces back through this correspondence between Alexandrov discrete spaces and preordered sets, the notion you get out is what one might call a retromonotone map. It sort of has the same kind of lifting flavor that we've seen in the previous few examples. So the idea here is if I have a point x in x, and I have a point y prime in y, and phi of x is less than or equal to y prime, then there should exist a point above y prime, so a point x prime above y prime, such that x is less than or equal to x prime. So this notion of retromonotone map of preordered sets corresponds to having open maps of Alexandrov discrete spaces, and then, I mean, you can combine them together, and so the open continuous maps of these Alexandrov discrete spaces are the lens-like notion in this setting. Okay. Okay, so this is the last example that I'm going to show you. This is more of a computer sciencey kind of example. So here we're talking about labeled transition systems, but I've put the generalized here because this example includes labeled transition systems, but it also includes some more things. And I mean, I don't want to sort of, there's a way of sort of seeing exactly how the labeled transition systems fit into this picture, but I mean, I'm just going to talk about these generalized ones because it's easier. So in this setting, we have some set of labels, which we usually, so I mean, okay, the setting where these are used is often like concurrency theory or something like that. And so you have interacting systems, and these systems can perform actions that have to interact with other systems. So we have a set where we think of the elements as sort of actions that systems can perform. And there's also a special action called the silent transition, which sort of represents internal actions that you can't see externally from the system. And so a generalized label transition system consists of a set of states, and for each, I mean, there's different ways of phrasing it, but say for each of these sequences of actions or strings of actions, you sort of have a relation on the set of states that says from if I start in a state and I do this sequence of actions, which state do I end up in? So for instance, so if alpha is one of these strings of actions, then x is related via alpha to x prime. Sort of what you interpret that as saying is if I start in state x, and then sort of this sequence of actions is performed, then I could end up in x prime. But so in this setting, whenever I start in a state, I can always get back to that same state via the tau action. And I mean, it should respect composition in the appropriate way too. So if I can get from x to x prime via alpha, and I can get from x prime to x double prime via beta, then I should be able to get from x to x double prime via alpha sequence with beta using the composition in this free monoid. So in the setting of labeled transition systems with one of these silent transitions, we have a notion of weak simulation. So the weak is referring to the fact that we're interested in treating silent transitions as sort of internal, as in not you can't observe them externally. But I'm just going to omit the word weak. And here, this functional. So normally simulations are relations between two of these transition systems, but we're going to say one of these simulations is functional if this relation is the graph of a function. So these functional simulations then consist of a map. So between the two transition systems, so a map between their sets of states, such that if in the domain transition system, I can get from x to x prime via the sequence of actions in alpha, then in the codomain transition system, I can get from f of x to f of x prime via the same sequence of actions alpha. So that's a functional simulation. Now, I've introduced this term retro simulation, but really this is just a simulation which is a function in the other direction. So a simulation is a relation. So you can say, well, what happens if I have a simulation where the opposite of this relation is a function, and that's what I'm calling a functional retro simulation. So here we again have a map between the states of two of these generalized transition systems, but now we have a lifting property. So for every state x in the domain transition system, and for every state y prime in the codomain transition system, if I can get from phi of x to y prime via the sequence of actions in alpha, then there should exist a state in the domain transition system corresponding to y prime, such that I can get from x to x prime via the same sequence of actions alpha. And so we have this, I guess, functor-like notion and this retrofunctor-like notion. When you put them together, you get what we might call a functional bisimulation. So again, in this setting, we have a notion of bisimulation, which is a relation between two transition systems where you can sort of go back and forth between them. But in this case, because the relations are both functions, you get a functional bisimulation. And these, they're important in the theory of bisimulations because every bisimulation can be represented as a span of these functional bisimulations. So that's my last example. So I hope at this point, you've seen a bunch of different examples that give you a feeling for what these retro kind of morphisms are and what the lenses can turn out to be. And the point of this talk, or the point of the work that Bryce and I did, was that all of these examples are examples of some overarching notion, and that's an enriched categorical notion. So what do these examples have in common? Well, it's enriched categories. So in order to define these retrofunctors, so normally you can do categories enriched in a monoidal category, but in order to define these retrofunctors, we need to ask that it's a distributive monoidal category. So in other words, our monoidal category should have coproducts, and the tensor product should distribute over the coproducts. And so in this particular setting, well, obviously we can define enriched functors in the usual way. So you have an object map between the object sets of the enriched categories, and for every pair of objects, you have these actions on morphisms. So FAB goes from the hom object of C from A to B to the hom object of D from F of A to, that should be F of B, that's a typo. And then on the so for, I guess this is the new, or one of the new things is the notion of enriched retrofunctor. So for enriched retrofunctor, we again have an object map from the object set of C to the object set of D. And then for the lifting maps, so you have for every object A of C and every object Y of D. So we have one of these morphisms that goes from the home object from phi of A to Y to this sum over all of the things in the fiber over Y of the home object from A to B. So this is encoding the lifting part of these morphisms, and obviously, I mean, these things have to satisfy certain axioms that encode the fact that that the identities and the composites are preserved. So this is a notion of enriched functor, enriched retrofunctor, but the reason why there's this typo is because I introduced an extra slide here to show the usual presentation of enriched functors. But what I wanted to do was show you this alternate presentation of enriched functors and sort of emphasizes the kind of duality between the two notions. So here you can see that, well, if we sort of take the co-product co-pairing of these morphisms over all of the B that are in the fiber over a given object Y. So you get a morphism from this sum to here. You can see that that morphism goes in the opposite direction to this morphism here. So it's sort of this lifting is just saying, well, we want these morphisms to go in the other direction. And then when you put a V-enriched functor together with a V-enriched retrofunctor, and you ask that they have the same object map, and you ask that when I do this lifting map, and then I do this action of the functor, if I ask that that composite is the identity morphism, then that's what a V-enriched lens is. So this is the enriched notion of delta lens, of retrofunctors between ordinary categories and delta lenses between ordinary categories. And the point is, if you pick the right base of enrichment, then you can recover the examples that I showed you already. So here's a table that sort of summarizes the examples that we saw. I guess the main point in this table is to have a look at what the bases of enrichment are that recover the notions that we saw. So obviously, for set, we get the ordinary notions of category, functor, retrofunctor, delta lens. For weighted sets, well, we get the weighted variants of all of those. For this, the real numbers between 0 and infinity, including infinity with the appropriate order, you get the Leviometric space examples. If I pick the interval category, so you think of the object as true and false, and the unique morphism, and the morphisms as like implication, then you get the Alexandrov discrete spaces, or the pre-ordered sets, depending on how you want to think about it. And if you look at, so if I have a set A, and I look at the free monoid on A, and then I look at the power set of that, that's the free quantile on A, with the appropriate order, you get this generalized labeled transition systems example. So I think that's quite interesting that this sort of enriched notion actually encompasses a whole bunch of examples that have this sort of feeling of having these lifts, which so that's pretty much the end of my talk. I don't know, how much time do I have left if I want to say a few words about what's in the paper? Okay, maybe I'll wrap it up here and we can open it up to questions. Do I? Yep, Alex?
Yeah, I just wanted to ask, is there a relation between these lenses and the lenses that like invariant functional programming, for example?
Yeah. So there's a whole bunch of notions that have been given the name lens, and this is because they all are generalizations of quite a very elementary notion, which is sort of, I guess, set-based lenses, where you have like, you know, a get function and a put function, and, you know, maybe or maybe not, you want them to satisfy some axioms. And then sort of over time, they've been generalized in different directions. And I guess this notion of delta lens is kind of an independent generalization to the kind of lenses that people at, for instance, Strathclyde talk about. But it would certainly be interesting if there was some way to reunify them under some, you know, even more general notion. But I mean, you wouldn't want to do it arbitrarily. It should actually be a unification that makes sense. But yeah, it's not the same thing. Yeah.
Thanks for the talk. Similar question about what the connections are. These retrofunctors look, I mean, if you squint, and especially in the topological example you gave, they look like having left adjoints. So I was wondering how far that connection goes. But for the Alexandrov space example, you have something which is a functor and a retrofunctor at the same time.
Where are we looking? This example.
Yeah. That this continuous map, open map, is the same as having a left adjoint to the inverse image functor.
Okay. Maybe we can discuss it and have a think about it. I don't see it straight off the top of my head, but also I'm maybe not in my thinking mode at the moment. I'm in talk mode. But this sounds interesting. I mean, I think Bryce, a previous talk, did someone suggest some connection with adjoints or something? Like it's.
Yeah, I feel like we've had this question before, but we've never actually thought about it.
Yeah. It would be cool if there were some connection there, but off the top of my head, I'm not sure.
I mean, the definition looks like in some special cases you will recover certain classes of adjoints.
That could be cool, but yeah, maybe we can just discuss it in the break.
Have you thought about what I'd like to know what the enriched version of retrofunctors is when you're enriching a cat? Like, what's the two categorical version of the
Okay. Have we thought about this? I feel like at some point we maybe.
It's not so interesting.
Okay,
it's what you would expect. Instead of just lifting the morphisms, you're lifting the two cells to a two cell above it, such that
Okay.
Yeah, I mean, there's lots of bases of enrichment you can try, but I think here I've selected out bases of enrichment where these retrofunctors and lenses give notions that people have been interested in previously. Whereas, yeah, I think what we decided was we sort of had a look at this notion where, oh yeah, you can do it, but maybe it's not so interesting, or we couldn't see a use for it, so we haven't really talked much about it. But you can certainly do it. Yeah. Cool. If there's no more questions, maybe that's it.